Dear friends, Mass Aspirants is a collective initiated by myself in 2017, and we have faculty members, research scholars, and students from all over India as members. We used to organize several online programs to help the math students. As a part of online problem solving session series, today we blessed to have Dr. Sushmitha P., Assistant Professor, IIT Patna, with us to handle a session on linear algebra. Dr. Sushmitha completed her Ph.D. from IIT Madras, and her broad research area is linear algebra and optimization. I am very happy to introduce Dr. Sushmitha, and I am sure that today's session will be really helpful to all those who are seriously preparing for competitive examinations like IIT, JAM, NET, and GATE, etc. I welcome everyone to this program. Welcome, Sushmitha.
Thank you, sir. Thank you for giving the opportunity. And I see that many people have benefited from the sessions that you are organizing. Thank you for that as well. So today I will focus mainly on the linear algebra part in JAM. Okay. So we will try to solve some previous JAM papers. In fact, I have collected the linear algebra questions in the past 4 years papers, 21, 22, 23, and 24. I have first listed down the questions, all the questions, based on which year they appeared, and then I have separated it topic wise. So why I have put it this way is because when we look at the question paper, we will get to know an idea of how much marks linear is dedicated to linear algebra, or what is the mark distribution in each of the topics. Like you have MCQ, MSQ, NAP. So you will also get an idea of how much is asked of linear algebra in each of these. That is why I've put them question paper wise first. So I will share this after the session is over. First, JAM 2021 was conducted by IISc. So the questions, the topics that we prepare and go, and what comes in the exam is all, they are not dependent. We may prepare something else may come in the exam. But yes, to have a, like, okay, yeah, at least this is one question that comes every year, something like that. That way, that is why we should look at previous year question papers, so that we will have an idea, okay, at least one question definitely comes from this topic, so I shouldn't skip this topic. That is the idea, to look at previous year question papers. And solving previous year question papers helps in getting the feel of an exam. That is also another reason why we should solve previous year question papers, or at least have a look at it. Okay, so JAM 2021 was conducted by IISc, and I have listed down the questions that they have asked. So in MCQ, there have been 4-5 questions. Five questions, and then 2022, IIT Roorkee had conducted. So based on which institute organizes, you will also see that there is a difference in the type of questions that is being asked. So see, there are 8-9 questions in MCQ in 2022. MCQ has 2 varied marks, I guess. One is 1 mark and the other is 2 marks. I've put all together. 2023 was by IIT Guwahati. 6 questions. 24 by IIT Madras. 5-6 questions. Okay, so in general, you have around 5 to 6 questions in MCQ. And then in MSQ, where you have multiple select questions, you have multiple right answers. I think it is 2 per year. Okay, IIT Madras had asked only one. So probably IIT Madras gave more linear algebra questions in some other some other subsection. So in NAT, IISc has asked 4 questions. IIT Roorkee 2 questions. Just so that you don't think it is biased, IIT Roorkee had asked a lot of MCQ questions. There were 9 questions. IIT Guwahati 4 questions and IIT Madras 5 questions. Okay, so IIT Madras had usually it was 2 MSQ, but IIT Madras had 1. But in NAT, instead of 4, they've asked 5. So that is, it is balanced in some sense. The total marks is overall the same for all years. The number of questions in each subsection may be a little different. Okay, so the first few pages that I showed is the set of all questions year-wise. But then how we are going to solve today is topic-wise. I have split the questions based on some broad topics, like for example, matrices. In this, there are questions based on simple matrix computations and eigenvalues related problems. So something related to eigenvalues, eigenvectors, or just computing determinant of the matrix, or some matrix solving matrix equations, etc. So all those questions I've put together. We will solve topic wise. So we will solve these first. And then in matrices itself, there is another subtopic, which is, I think, the rank of matrices, calculating rank of matrices. So see, there is rank related questions. So why I have split it topic wise is because if you look at these questions in terms of these topics, I've also mentioned which year and what kind of a question it was. So we will have an idea if such type of question is repeated every year and all that. So there is a question on rank, things related to rank of a matrix almost every year. And then you have system of linear equations. I think there is definitely a question based on system of linear equations in every year. At least one question. So there are different questions. And then another broad topic is vector spaces. So matrices, you have certain questions, and then vector spaces. So in vector spaces, asking whether the given options are subspaces or not, that is one thing that I saw repeatedly. And then certain questions on span and linear dependence. Then dimension, there is definitely one or even 2 questions based on dimension of a subspace. So you can see that there are multiple questions based on dimension. Then another broad topic is linear transformations, giving options and checking whether the options are linear transformations or not. These are really simple questions that you should make sure that you attempt. And then based on range, null space, or just by using certain properties of linear transformation, there are some questions. And then rank nullity theorem. So using the rank nullity theorem, there is at least one question every year. So these are the broad topics classified. I thought we will focus on solving matrix related questions today. We will try to cover as much as possible. How much ever is possible, we will cover. And I will share this PDF with you so that you have a list of linear algebra questions of the past 4 years with you. Okay, let's quickly start solving them. So please stop me if at any point you feel that you have a doubt, if something is not clear, or you can also tell me if you already know how to solve and if it is pretty simple so that we can skip. And if it is interactive, it will be better so that we will have an idea of what you are expecting. Okay, so that we will not waste time in case something that is already known to you is being discussed in detail. Okay. So one thing, based on how we want to look at this question at the exam hall, that is one thing. Another thing is knowing the concept and solving the problem. So if you know the concept, obviously you will be able to solve the problem, but then applying tricks and solving is what is going to help you solve it faster. Okay. So we will try to see where we can apply tricks, and we will try to approach in both ways, concept and how to solve it fast. Okay. So this one question, this was in 2022 as an 2021 as an MCQ. So there is only one right answer. So and in MCQ, if you notice, there is always at least two of such questions where you'll be given two statements and then you have to check whether they are true or false. So in this case, you don't have a choice. You have to try to understand both the statements and then solve both. Only then you will be able to answer such questions. There are questions where you can eliminate the options and then get the right answer. But then in this case, you cannot do that. You have to know everything about both the options. Only then you can answer this question. And on top of that, MCQ has negative marking also. So you have to...
Sushmitha, excuse me.
Yes, sir.
Could you zoom the screen a little bit so that...
Okay, sure. Is this fine?
Yeah, now it's very fine.
Okay. Okay, so since you have negative marking, you should also be careful not to hit negative marks, because even less number of positive marks is okay, but then if you have negative marking, that's going to pull your rank down. So even half a mark is going to matter a lot. So you have to make sure that you don't unnecessarily answer questions and get negative marking. So, okay, let's solve. So the question here is, let n greater than 1 be an integer. Consider the following two statements for an arbitrary n cross n matrix A with complex entries. Okay, so you have a square matrix. If A power k is identity for some integer k, then all the eigenvalues of A are the kth roots of unity. Yes, anyone has anything to say? Okay, so the first statement is A power k is identity, then all the eigenvalues of A are the kth roots of unity. The second statement is, if for some integer, all the eigenvalues of A are the kth roots of unity, then A power k is identity. Okay. So the two statements are like converse of each other. The first one is A power k is identity, then the eigenvalues are the kth roots of unity. And the other one is, if the eigenvalues of A are kth roots of unity, then A power k is identity. Okay. One thing, before solving, let's quickly define what an eigenvalue is. So you can define eigenvalues for square matrices. Eigenvalue is nothing but any scalar that satisfies this equation for some non-zero x. So lambda is said to be an eigenvalue of the matrix A. Lambda is a scalar from the field, underlying field. So lambda is an eigenvalue for A if there exists some non-zero x such that Ax is equal to lambda x. So basically, to find the eigenvalues of the matrix, what you will do is you have to solve equations of this kind. So we can write this as A minus lambda I times x is equal to 0. You want a non-zero x satisfying this condition for some x not equal to 0. So this is nothing but a system of linear equations, right? It is a homogeneous system of linear equations, and you want a non-zero solution for this homogeneous system, right? A homogeneous system has only two solutions. Homogeneous system. Homogeneous system means what? Ax is equal to 0. This is homogeneous system. When the right-hand side vector is 0, it is a homogeneous system of linear equations. Any system of linear equations has either a unique solution, no solution, or infinitely many solutions. So you know how to solve and find out by writing down the augmented matrix and all that. For a homogeneous system, you have only two cases. So there is always a solution. No solution case is not possible. X is equal to 0 is always a solution. So there is a unique solution or there are infinitely many solutions. Unique solution means X is equal to 0, right? Unique solution means there is only one solution, and we know X is equal to 0 is always a solution. So for a homogeneous system, if there is a unique solution, then X has to be equal to 0. Otherwise, you have infinitely many solutions. So if there is even one non-zero X as a solution to Ax is equal to 0, then there are infinitely many. Now, if the homogeneous system, if the matrix is a square matrix, if it is a square matrix, then we know that there is a unique solution if the determinant is not equal to 0, right? When the matrix is invertible, in fact, any Ax is equal to B. If the matrix is invertible, then A inverse B is a solution. And that is the unique solution whenever the matrix is invertible. So here again, unique system, unique solution means that the matrix has to be invertible. So if it has infinitely many solutions, then the determinant has to be equal to 0. So if you look at this system, if we come back to this eigenvalue problem, Ax is equal to lambda x has to be satisfied for some non-zero x. So that is equivalently A minus lambda I x is equal to 0. This homogeneous system should have a non-zero solution. Non-zero solution means we are in this case, infinitely many solutions case. So the determinant has to be 0. So determinant of A minus lambda I has to be 0. If you solve for this, you will get the eigenvalues. Solve to get eigenvalues of A. So if you solve, determinant of A minus lambda I is equal to 0, where lambda is the variable. So this is called the characteristic equation. You will have an equation in lambda. When you solve, you will get the eigenvalues of A. Whatever different values of lambda you get, that will be the eigenvalues of the matrix A. Okay. So we have this. We are talking about eigenvalues here. Eigenvalues of A and what we can tell about A power K. So let's just notice one thing. If Ax is equal to lambda x, x not equal to 0, then what can we tell about A squared x? Can anyone tell me what we can tell about A squared x?
Lambda square
Lambda
x.
square x.
Yeah, so we can write this as A of Ax, and Ax is lambda x. Lambda is a scalar, so I can take it out. So this is lambda times Ax. Ax is again lambda x, so we get lambda square x. So if lambda is an eigenvalue of A, lambda squared is an eigenvalue of A squared. Okay. So in general, if lambda is an eigenvalue of A, lambda power K is an eigenvalue of A power K. But the question here is not this. It is the opposite, right? So you're given something about A power K. We know something about A power K. We are asked about the eigenvalues of A. So A power K is identity. A power K is identity means, so this is one thing. A power K is identity means A power K times X is going to be Ix, which is equal to X, which means that 1 is an eigenvalue of A power K. In fact, 1 is the only eigenvalue of A power K. Right? Because no A power K is identity. So no other lambda satisfies A power Kx is equal to lambda x. So 1 is the only eigenvalue of A power K. Now the question is, what can we tell about the eigenvalues of A? Can we tell the opposite? If lambda power K is the eigenvalue of A power K, can we say that lambda is an eigenvalue of A? Okay, so that's one thing. So let's look at the statement again. If a power k is identity, then all the eigenvalues of a are the kth roots of identity. So can we go back in this? So here what we had was this implies this. So in general, this is the implication. Can we go back? Can we say a power k x is equal to lambda x? Does this imply ax is equal to lambda power 1 by kx? Do you think this will be true?
This
Yes,
is true for if A is invertible, I think.
Okay, A is invertible in this case. No, a power k is identity. Then what
Yeah,
happens?
A is invertible.
Okay, so yes, we can go back actually. A power k is identity. Then all the eigenvalues of A are the kth roots of identity. In fact, you can check this way, right? If to check A implies B, you can also check not B implies not A, right? The contrapositive statement. You can check that way and you can tell that this is actually true. A power k, if the eigenvalues of a power k are all 1, then the eigenvalues of a are 1 power 1 by k, the kth roots of unity. Okay, so this statement will be true. What about the second statement? If for some integer all the eigenvalues of a are the kth roots of unity, then a power k is equal to identity. So what happens there? If ax is equal to lambda power 1 by k of x, then can we say a power k is identity? Where lambda is 1 actually. Kth roots of unity. See what happens according to this statement. According to this statement, if lambda is an eigenvalue of a, lambda power k is an eigenvalue of a power k. So what happens here? Lambda power 1 by k is an eigenvalue of a. So lambda power k is an eigenvalue of a power k, right? But lambda power k is 1, right? Kth roots of unity means 1 power 1 by k. So the kth power of that is equal to 1, right? 1 is an eigenvalue of a. But if all the eigenvalues of a power k are 1, can I say that it has to be the identity matrix? That is the question, right? The conclusion is a power k is identity. Can we say that? What we conclude from here is if A has kth roots of identity as its eigenvalue, we know that all the eigenvalues of a power k have to be 1. Can we say that it will be equal to the identity matrix?
Yes. Here we have.
No, ma'am.
Hello, ma'am.
Yes,
ma'am.
I
You
can
can
hear.
say. So here they have given that all the eigenvalues of A are kth roots of unity. And every such root will kth power of every such root will be 1. Is that why you're saying all roots of A power k is 1?
Yes, yes.
Okay.
If lambda is an eigenvalue of a, then lambda power k is 1. That is what this means, right? All the eigenvalues of a, that is, you take any lambda, it is a kth root of unity. That is lambda power k is 1.
Hello, madam. I think the logic will be like that. Since a power k has all the eigenvalue 1, let's go to the eigenvectors. They are basically the k, all the kth roots of the unity. They are eigenvector associated with all the kth roots of unity. And we all know that the eigenvector associated with distinct eigenvalue, they are linearly independent. So we have n number of linearly independent eigenvectors. So with respect to that basis, A will be a diagonalizable matrix, and that diagonal matrix will consist all those ones.
Okay.
Yeah, isn't it? So P inverse AP, that will be a diagonal matrix which all entries are 1. So that will be an identity matrix. So that from there we can conclude that A to the power k will be identity.
All right. Okay. So this is exactly why this question was posed, probably, that we think of it this way. But then see, the statement says that all eigenvalues of A are the kth roots of unity. It does not say that all the kth roots of unity are eigenvalues of A, right? With what you said,
Yeah.
you have assumed that all the kth roots of unity are eigenvalues of A. So if I take A to be this matrix, say 1, 1, 0, 1, the eigenvalues of A are 1 and 1, right? And the second statement means the if part of the second statement is satisfied, right? All the eigenvalues of A are kth roots of unity. In fact, they are all 1, 1. So if I can take any k, say, let's take A squared only. Second root, are these second roots of unity?
No, they
Yes,
are
right?
square. No, second roots of unity means
1
x
power
square
1
is
by
equal to
2
1.
is what?
A
So you
square is
have
equal
1
to
and
1.
minus 1, right? These are the square root of 1 and minus 1, right? Sorry, 1. Square root of 1 is 1 comma minus 1. So these satisfy that condition, right? Kth roots of unity means what? Power k has to be equal to 1. So 1 squared is 1. Again, 1 squared is 1. The statement does not say that all the kth roots of unity are eigenvalues of A. So all kth roots of unity are eigenvalues of A. This is one thing. All eigenvalues of A are kth roots of unity. This is another thing. So in this case, A should have 1 and minus 1 as eigenvalues. Say if I take this case. But in this case, I'm allowed to have 1, 1 as eigenvalues of A, or minus 1 as eigenvalues of A, 1 minus 1 as eigenvalues of A. Right? You see the difference?
Yeah.
So in this case, I think we have got a counter example, right? So here, if this is A, then A squared is what? 1201, I think, right? Yeah. In fact, any A power k will be of the form 1k01, right? So this is never identity. A power k is never identity. But all the eigenvalues of A are kth roots of unity. They are just 1, right? So is it clear? See, whatever you said was this. If the statement had all kth roots of unity are eigenvalues of A, then whatever you said was true. The matrix will be diagonalizable. In fact, all the eigenvalues are distinct, so the matrix is obviously diagonalizable, which means that it has to be the diagonal matrix and all that. So We have to read the statement carefully, try to understand what is given. Like, we shouldn't miss out on the details. See, just a small word play, and then we get two different statements, which gives two different conclusions. We have to be very careful when we read the question.
Okay.
So is it clear to everyone that the second statement is not true, and we have got a counter example? So this is not given.
Ma'am, but if we just take the so it is give first line here. So it is given that a power kx is equal to lambda x, and we
Which statement are you talking about? The second statement, is it?
yeah. In the second statement, we are given that ax is equal to lambda power 1 by kx.
Yes.
Right? And we are checking if a power k is I. That is same as checking a power k times kx is equal to x for every x. Oh, okay. Yeah. So it's for every x.
Here I have given a counter example. No, for this matrix, a power kx is not equal to x. Okay, so this is
I mean, second statement. If all eigenvalues of A are ith root of unity, then this will happen, ma'am. If
no, so that is what is given. No, all eigenvalues of A are the kth roots of unity. That is given. That
madam, if
for
the
that
given
only we
is
have given a counter example.
okay, madam.
The statement when it will be true is if all the kth roots of unity are eigenvalues of A.
Then A power k equal to in.
Yeah.
Okay, madam.
Because in this case, you will
Ma'am,
have different eigenvalues for A, right?
Hello, ma'am.
Yes.
Ma'am, in first statement, we can take A is equals to identity matrix. Then identity matrix has eigenvalues only one. That are not
that's fine. No, one is a
unity.
kth root of unity. No, again the same thing. No, see, the first statement does not say that. It's just telling what the eigenvalues of A are. They are kth roots of unity in the sense that all the eigenvalues of A should satisfy lambda power k is equal to 1. It does not say that all the eigenvalues of A are all the roots of lambda power k equal to 1. Right? If A power k is equal to identity, okay, we can take it in the diagonalizable form itself. A power k is equal to identity means A power k is okay, I don't think it makes any sense writing it that way. P inverse I P. Okay, this way I don't think it is going to help us. A power k's identity means all eigenvalues of A power k are 1. So now I have to check what happens to the eigenvalues of A. So let's take A squared. Say if k is equal to 2, then if A squared is equal to identity, then eigenvalues of A squared are 1, 1 comma 1. Say I have a 2 cross 2 matrix, then the eigenvalues are 1 comma 1. Now what happens to the eigenvalues of A? That is the question. So what they are saying is eigenvalues of A are kth roots of unity. So what can we tell about the eigenvalues of such a matrix? I want to find out what is Ax is equal to lambda x. What all lambda satisfy this condition? I know A squared x is equal to x. So what can we do in this case? See, I know A squared x is x. So A times Ax is equal to x. This I know. But what is Ax? It is lambda x, right? Lambda x, A times lambda x is equal to x. So this is lambda times Ax is equal to x. So I have lambda squared x is equal to x. So I have lambda squared is equal to 1. That is what I want, right? If lambda is an eigenvalue of A, lambda squared is equal to 1. So this means lambda is a kth root of unity, right? Second root here, in general, kth root of unity. Am I correct?
Ma'am, lambda or lambda square is the kth root of unity?
Lambda, right? Lambda is the kth root of unity means lambda power k has to be equal to 1. Right?
Yes, ma'am. It's okay.
Kth root of lambda is 1 power 1 by k. K is 2 here. So 1 power 1 by 2. Which means lambda squared is 1. So this will be for the first condition statement, and this is for the second statement. So the first statement is true, but the second statement is not true. Okay, is it clear?
If we change,
Huh.
madam, if we change second question, if for some integer k greater than 1, all the eigenvalues are A are kth root of unity.
Then a
All
power
kth
k will be
kth
1.
root of unity. If we change the question, all kth root of unity are the eigenvalues of A, then how can we say that A power k equal to In, madam? We can say it is diagonalizable. How
Yes.
can we say it is diagonal?
Ma'am, actually k is not equal to n, and a has index n. So we can't say about anything.
Okay, okay, fine. Yes, even then we cannot say. Agreed. So if k is equal to n, only then we can say, right? Yes. Okay. So even if A, all the eigenvalues of A are all the kth roots of unity, then A is diagonalizable with the diagonal entries being all the kth roots of unity. Yes, but we cannot say that A power k is equal to identity. But it just says for some integer, right? So I can choose that integer k to be equal to n, right? Then it works, no? For some integer, this is satisfied, it says. So I can choose k is equal to n, and it works in that case, right?
But
This
only for
happens
k is
when
equal
A
to
power
n case.
k, if k equal to n, then we can say A power n equal to,
Identity.
how can we say that A power n equal to In? Ma'am, we can say A power n equal to diagonalizable, will have distinct eigenvalues. This is necessarily true, madam. Equal to In.
If eigenvalues of A are lambda, then eigenvalues of A power k are lambda power k, right?
Yes, ma'am.
So eigenvalues of A I know now are the kth roots of unity. So A power k will have all eigenvalues as 1, right?
Yes, madam.
So from there we can tell, no?
Madam, all eigenvalues are equal to 1. That doesn't mean that not equal to In. No?
No. All eigenvalues are 1 and it is a diagonal matrix, no? So it has to be the identity matrix.
How it is not necessarily to be diagonal, no, madam.
So say I have a diagonal matrix. So I'm not taking any power. I'm just telling in general that I have a diagonal matrix. Inverse. P inverse dp. And I know that all the eigenvalues are 1. Right? So if I know all the eigenvalues of A are 1, then I know that all eigenvalues of D are 1, right? And D is a diagonal matrix, right? So D has to have all its eigenvalues along the diagonal, and it is a diagonal matrix, which implies D is equal to identity, right? Implies A is equal to identity, right? I just substitute identity in the place of D, I'll get A is equal to identity. Right? So if I have a diagonalizable matrix, all of whose eigenvalues are 1, then it has to be the identity matrix.
Ma'am, we can here
Madam,
you
we can
are
consider
saying
upper
A to be
triangular matrix.
diagonalizable because it is invertible.
What is it?
If A is a diagonalizable matrix, then the arguments are fine. How do you know that A is a diagonalizable matrix?
I am telling that only here. If A is diagonal. Oh, you're asking in this statement?
Yeah,
in
because it is.
If I take all the eigenvalues of A are the nth roots of unity, all the nth roots of unity. Nth roots of unity, you have n distinct nth roots of unity, right? So distinct eigenvalues means the matrix is diagonalizable, right?
Yeah, okay.
So that way.
Madam, A power K can be equal to the diagonal upper triangular matrix. May be equal to, madam. Upper triangular matrix with all entries are 1. Diagonal entries are 1.
But then you also have this, no, that what was it? Okay, so you're saying A power K.
Why should be IN? It can be upper triangular matrix, non-diagonal upper triangular matrix with all entries of it diagonal equal to 1. Is this possible?
You're asking if A power K can be, say this, right? Say A
Yes,
square.
madam. In A square, it does not happen, madam. I check it now.
This is not going to happen for any A power K, right? Because for A power K, it is going to be like this. 1, when you take powers of this matrix. Now, what was the question?
Diagonal eigenvalues are exactly equal to nth root of unity.
All the eigenvalues are all the nth roots of unity, right?
Yes, ma'am.
So you have distinct eigenvalues, right?
Yes, ma'am.
So A becomes diagonalizable.
Yes, ma'am. A power, yes, ma'am. A becomes diagonalizable.
If A is diagonalizable, then A has to be the identity matrix, no?
No, actually,
A
madam,
not be A power
madam,
K.
Madam, he is telling that in the diagonal matrix D, all the diagonals has not been 1. It is the kth roots of unity. So it will be of the form 1, omega. Let's say.
Fine. Okay. Here I
1
wrote
omega
A.
omega square. That will be like that.
So this is like this.
Yes,
Omega
exactly
power
same.
n minus 1. Right?
Yeah.
Now what will be A power K? Is A power K diagonalizable?
Yes, ma'am. Diagonalizable.
Yeah, because if A is diagonalizable, A power K is diagonalizable, right? What will be the eigenvalues of A power K?
All equal to 1. 1 n times.
Yeah. So by this argument, now A power K becomes identity, right?
Yeah.
Madam, eigenvalues are equal to 1. That doesn't mean, how it mean it equal to identity, madam?
So that's what I wrote here. If I have a diagonalizable matrix, I can write it down like this, right?
Yes, ma'am.
And I know all the eigenvalues are equal to 1, right? So if it is diagonalizable, then the eigenvalues of A and the eigenvalues of D are the same, right?
Yes, madam.
So all the eigenvalues of D are 1, and it is a diagonal matrix, which means D has to be the identity matrix, right? And if I plug that in, I get A is the identity matrix. In this case, we are talking about A power K.
Yeah.
Okay, madam. Understand. Thank you.
Ma'am, instead of using diagonalizability, we can just look at the characteristic polynomial. Since we have n distinct roots, the characteristic polynomial is just the product of all those factors, and that factor will be x power n minus 1. So then a has to satisfy it. So a power n is equal to identity. Here we have taken k to be n, so
yes.
works fine.
And the same thing can be said on the first option. Since a to the power k is equal to identity, so the analytic polynomial will be of the form x to the power k is equal to 1.
Yes.
So x minus 1 into some x to the power k minus 1 plus dot 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 that thing. So in that case also we can say that all the eigenvalues are the kth roots of unity.
Yes. You can use the characteristic polynomial also.
Yeah. So so that will be much more simpler argument, I think.
Yeah, if you use you cannot use the diagonalizability always, right? You can use the diagonalizability only if we know that all the
k is equal to n.
kth roots of unity are repeating. Yeah. So that was someone's question. That is why I use the diagonalizability. Otherwise, you cannot use that. Because here it just says all the eigenvalues of A are kth roots of unity. It can be like that second case, no? Like this example, where the roots are repeating. Yeah. So a general argument will be something like this. Something like this, where you don't use the diagonalizability. But of course, if you have distinct eigenvalues, then the matrix is diagonalizable. We can use that fact. So is there any questions on this? I think this includes a lot of things that we need to know about diagonalizability and eigenvalues.
But even if you want to use characteristic polynomial idea in the first statement, we only know that x bar k minus 1 is a polynomial satisfied by A. Then we should have an idea that any polynomial satisfied by A is going to be is going to divide characteristic polynomial. If people don't know that, then they cannot conclude that kth roots of unity are going to be the eigenvalues of A.
Yeah. So the easiest way to attack such problems is go by the traditional Ax is equal to lambda x and then try to see what happens. Because here we are not using characteristic, we are just using the definition of an eigenvalue. Ax is equal to lambda x and then how matrix multiplication works. That's it. Means to calculate powers. So if we just go by this idea, we will be able to solve the problem even without using the characteristic polynomial or diagonalizability. We needn't use anything. In fact, you just need to know Ax is equal to lambda x. Lambda is an eigenvalue, then Ax is equal to lambda x.
Ma'am, can you explain the second one, please, again?
Okay. For the second one, if for some integer k greater than or equal to 1, all the eigenvalues of A are kth roots of unity, then A power k is equal to identity matrix. So they are saying that all the eigenvalues of A are kth roots of unity. So if I take this matrix, A is equal to 1, 1, 0, 1, then its eigenvalues are 1 and 1, right? If I take k is equal to 2, then these are the second roots of unity, right? Second roots of unity means what? 1 power 1 by 2, square root of, I have to check what 1 power 1 by 2 is. It's 1 and minus 1. Both of these roots are second roots of unity. 1 is one of the second roots of unity, right? So it satisfies this condition. Now, does this imply A power k is equal to identity? So A power k, k is 2. I have taken k is equal to 2. So A squared is equal to, when we calculate the square of this matrix, we get this. This is not equal to identity, right? So the second statement is not true. So what is given is all the eigenvalues of A are the kth roots of unity. So you can just pick random kth roots of unity. Another statement which would have made the second statement true is all kth roots of unity are eigenvalues of A. So in this case, you have to pick all the kth roots of unity, 1 and minus 1. In this case, the statement would have been true by the argument that we were talking about here.
Oh, okay, ma'am. Thank you.
Huh. Okay, so is this clear? Is this question clear?
Yes, madam.
Okay, so let's proceed. So another MCQ 2021. Let A be an invertible n cross n matrix and C be a nilpotent matrix. So what is a nilpotent matrix? Invertible matrix means A inverse exists. Nilpotent matrix is
A power k is equal to 0 for some.
yeah. C power k is equal to 0 for some k. So this is a nilpotent matrix, and index of nilpotency is the smallest such k. Smallest k satisfying this condition is called the index of nilpotency. So if you have a nilpotent matrix, you have C power k is equal to 0. So just talking about nilpotent matrices, is every nilpotent matrix diagonalizable?
No, ma'am.
No. Okay. If a nilpotent matrix is diagonalizable, what should that matrix be?
Zero.
The zero matrix.
Yeah. So just by a similar argument, if A is diagonalizable and if all the eigenvalues of A are 0, if you have a nilpotent matrix, all eigenvalues are 0, right? So if all the eigenvalues are 0, you just replace, you will show that D is 0 and hence A is 0. So if a nilpotent matrix is diagonalizable, it has to be the 0 matrix. And another thing to be noted is all eigenvalues of a nilpotent matrix are 0. Okay, so these are not required for this question. I just mentioned it here. So you have an invertible matrix and a nilpotent matrix, and then you have a 2n cross 2n matrix. So you have block matrices. X11 is an n cross n matrix, X12 is an n cross n matrix, like that. That commutes with this matrix. Commutes means what? AB is equal to BA. That is satisfied, right? So you have two matrices that commute. X and B commute. XB is equal to BX. So then what can we conclude about X11, X12, X21, X22? Okay. So we have to take a look at what the equations are. And this is an MCQ, so only one is right. Okay. So you just have to write down what is X, what is B, and then see what happens. So you have X11, X12, X21, X22 into A0, 0C is equal to A0, 0C times X11, X12, X21, X22. So this is what is given. We have to infer something about all the X11, X12 and all that. Okay. So this is block matrices. So you can do block matrix multiplication, just like how you usually multiply. So X11A plus 0. This is the first entry here. X11 into 0 plus X12 into C. X21 into A into X22 into 0, X21 into 0, X22 into C. So this is the first matrix. The second matrix is AX11, AX12, 0, CX21, CX22. So this is what we have. From this, we have to conclude which are the 0 matrices. Okay, so we have 4 matrix equations. This we have, and then X12C is equal to AX12, X21A is equal to CX21, X22C is equal to CX22. Okay. So now what happens is you have 4 options. Which of them are necessarily 0? Necessarily 0 means you cannot choose anything other than 0 for those, right? So you can try other matrices for X11, X22 and then see whether it is still true or not. So one way of checking which is the right option is by actually calculating it and checking the right option. Another way is eliminating all the wrong options, right? So you have 4 equations, and then you want to see which one of them has to be necessarily 0. Now, if all of them are 0, then there is no problem. It satisfies all the equations, right? x11, x12, x21, x22, if all of them are 0, it is still satisfied. But is it necessary for x11 to be 0? What happens if x11 is identity?
It is true.
There's no problem, right? It's not going to create a problem if x11 is identity. So this eliminates 2 of the options, right? This is wrong, this is wrong. x11 need not necessarily be 0. It can also be identity. Similarly, x22 can also be identity, and there is still no problem, right?
Yes, ma'am.
So in this case, we have eliminated 3 wrong options. So there is only 1 right option left. We cannot take x12 to be identity, because if we take x12 to be identity, then C becomes equal to A. That is not possible. No, C is an nilpotent matrix, A is an invertible matrix. An invertible matrix does not have 0 as an eigenvalue, right? And a nilpotent matrix has only 0 as an eigenvalue. So it is not possible that A is equal to C. So x12 cannot be identity. And similarly, x21 also cannot be identity. So you cannot apply the same logic for x12 and x21. But you can also prove that these have to be 0. It is easy actually. So you can take x12C, right? So I know C is a nilpotent matrix. So I will just multiply this with C power k minus 1. If C power k is 0, if C is a nilpotent matrix such that C power k is 0, I am just multiplying this with C power k minus 1. So now I have this is equal to 0, right? Because this is x12 C power k. And C power k is 0, so I have this. Now I will replace x12C with A times x12. Because I know x12C is A x12. And then I still have this C power k minus 1. I can now write this as C power k minus 2. And again, I will replace x12C with A x12. So that becomes A squared x12 C power k minus 2. Like this, if I keep doing, I will end up with what? A power some... I think A power k x12, right? You just keep doing this at each stage. You will get A power k x12, but this is equal to 0. And A is an invertible matrix. So I can multiply with A inverse power k into A power k into x12. This has to be equal to 0. So this means x12 has to be 0. So even by proving, you can show that x12 has to be necessarily 0. Or another way of solving was what we did first, eliminating the wrong options. So it will be wiser to use the first way of solving, because that saves so much time, right? Whenever you have questions related to matrix equations, you can always try out identity matrix and 0 matrix. Most of the options will be eliminated by these 2 matrices as counter examples. So whenever there are matrix equations involved, it is always wiser to try to eliminate options. Okay, is there anyone with a question in this? I think it is pretty straightforward and
Yeah.
It was easy to understand. Yeah. Okay. So this is a 2022 MCQ. Consider a 2 cross 2 matrix M, and M is given. If M power 8 times 10 is XY. Okay, I think I've missed the question. What is X, or what is Y, or what is X plus Y, or something related to X and Y. Okay. So what is your approach to solve this problem? Obviously, calculating m power 8 is a tedious task. So what do?
We can find characteristic polynomial and then it will be a power m square. Then we can multiply m power 4 or something.
But that is also a tedious task, no? Why would you want to find the characteristic polynomial at all?
Yeah, m power 8 calculation is here very easy. So just simply do it.
No, even m power 8 calculation is it easy? I don't know. See, multiplying two matrices is more difficult than multiplying a matrix with a vector, right?
Ax equal to lambda x.
Okay, you can try to find the eigenvalues, but do we know the eigenvalues straightforward from here? Even for eigenvalues, you have to do 1 or 2 steps, right?
Yeah.
See, m power 8x, or okay, m power 8, 1, 0. What does multiplying the vector 1, 0 to a matrix do? See, if I have A is equal to A, B, C, D, what does multiplying A with 1, 0 do?
Gives the first
column.
To get a column vector.
Just the first column.
Yeah, when you multiply with 1, 0 on the right side, you're going to get the first column. When you multiply with 0, 1, you'll get the second column, things like that. So this is what you're going to get. Finding A squared is difficult, but then finding A squared 1, 0 is easy because you can just do A times 1, 0, right? So that will be the easier approach. Instead of doing matrix multiplication, you will do matrix vector multiplication. So m power 8 times 1, 0 is nothing but m power 7 times m 1, 0. And you know what m 1, 0 is? The first column of m 1, 1.
Yeah.
What happens when you multiply a vector with 1, 1?
With the addition of columns.
You just add both the columns, right? A plus B, C plus D. That's what you do. So this is m power 6 times. You just add both the 2, 1, right? Now what you do is m power 5 times. 2, 1 means you're multiplying the first column with 2 and the second column with 1. Means you needn't think so much. You can just do m2, 1. You will get that. So this way, you're doing much lesser calculation than actually finding out the entries of m power 8. In fact, you don't need all the entries of m power 8. You just want to have some relation, means you want some connection between in some sense, you're more focused on the first column, right? But eventually, yes, you are using the other columns as well. But then matrix vector multiplication is easier than matrix multiplication. And all the time, when you do this calculation, you're just going to keep using this m. If you calculate m squared and then m cube and all that, you're going to keep getting values which are bigger and bigger, right? But then every time when you just have to multiply the matrix m with a vector. Yes.
Ma'am, I'm not able to understand the step m raised to the power 6 to 1.
So that's what I've written here, no? It is equal to m power 5 times m to 1. So you just have to evaluate this part. So this is m power 5 times m to 1. You just have to multiply m with 2, 1. That is going to be what? 2 plus 1, 3, and then 2. So again, to find out m power 5 times 3, 2, I will do m power 4 times m 3, 2. And m 3, 2 is easier to calculate.
5 to 1.
So this is what? 5, m power 4 times 5 and then 3. Right? Again, the next step. What would the next step be? The idea is to do matrix vector multiplication.
Yeah. In a similar
MQ times 8, 3.
M power 3 times M 5 3. So this is what? M. What does M do? It adds both the elements of the vector, and then the second one is the first component alone. So M power 3 times 8 5. Again, this will be M squared. What is it? Is there a question?
13. This will be 13.
Recursive equation. We are just adding columns, rows.
So what M does to a vector is, you just have to find out what M does to a vector. This is what x plus y and then x. So you have to add both the components, and for the second component, it is the first component of the vector. So once you understand that, it's still more easier. 13 and then 8. And then this is M times
21,
M.
13.
Yeah, whatever that number is.
So the answer will be 21 plus 9 and 13.
13 plus 8 is what? 21. Okay. 21, 13. So M of this is
34, 21.
Yeah. So I think I've written down the answer as 34. So I think they were asking for X. Yeah. So instead of, you see, you get why this is simpler than calculating M power 8, right?
Yeah.
So to calculate M power 8, you have to multiply M so many times. But then here you just have to multiply it with the vector that we get at each stage. And we also have seen what M does to a vector. So once you realize this, it's going to get much, much simpler. Okay. So the next question. So this is again like you have two statements and the options are which of them is true, false and all that. So you have to understand both the statements and try to solve. Okay. So you have given any two square matrices of order 2, define, okay, they are defining some function. A bracket of xy means x into y minus y into x. Let 0 denote the 2 cross 2 0 matrix. Consider these two statements. You have to evaluate both and then you have to see which is true, which is false. I think you can do this on your own, no? You just have to expand.
Yes.
Wherever there is this bracket function, you have to apply xy minus yx. The first entry of the bracket into the second entry minus second entry into the first entry, and then you should be able to do this. Okay, so, and one more thing, when you look at something, you should be in some sense able to feel which is true, which is false, especially when it comes to true or false statements. So any guesses which one is true, which one is false?
I think first one is true.
And the second one?
Second one is also true.
No, you can see, no, the second one cannot be true because it is not symmetric, no? One is having a plus and the other is having a minus, and you're bringing in a third element. There'll be many terms which are there here, which are not there here.
Okay.
See, you'll have an XZ term, but then here you won't have XZ at all, no? Because you'll have here it is YZ minus ZY. So,
second one is not true.
Yeah. So the first one, you're adding all such possibilities. So because of the plus minus thing, it is all going to get cancelled out. But you cannot just guess an answer. Obviously, you should work it out. But for the intuition, I'm saying. Okay. So the first one is true and the second one is actually false. Okay.
Ma'am, how can we do it easily in exam?
No, there is no easier way. For this, you have to work out because there is no trick involved. No, there is a new function that is defined there. So you just have to, one thing is when you keep in mind that you have to solve it within this time frame. You also have to keep in mind that you will solve it the fastest when you do it correctly in your first attempt. And even when you have your rough sheets, instead of scribbling in one corner, I would suggest that you write it down neatly so that you can, even if you think something is wrong, you can go back and see and you needn't work it out again. So for example, if you want to solve this, you have these three terms and then you have to put it equal to 0. So you first expand the second terms in the first go itself, like yz minus zy plus y times zx minus xz plus z times xy minus yx. So you have to write it down neatly, and don't write it in two different lines because this is going to have a lot of calculation. Write it neatly and clearly. Don't rush, because if you rush, you might have to solve it a second time with proper less speed. So it is enough. It is okay if you see, these are questions where you will definitely get the right answer. You are not going to get a wrong answer unless you make a careless mistake. So to avoid the careless mistake, you have to write it down neatly and take time. Don't rush on such questions because you know that you can score marks here. So that is one thing. Even the trick to solving, getting maximum marks is when you attempt all the questions in the question paper at least once. But at the same time, just because you want to attempt all the questions doesn't mean that you rush and try to solve and make mistakes. So patiently try to solve it. Again, as I mentioned, you can score the highest when you have read all the questions in the question paper at least once, because there might be easy questions at the end of the question paper. So you have to make sure that you are reading all the questions at least once. Yes, someone had a question. What is it? Okay.
Ma'am, what I think is, I mean, we are in second statement, it is like associative law. So, and our function is, I mean, our function is subtraction. So, subtraction is not associative. We can just contradict like that now. In the way of we are just guessing and just eliminate the second part because negative sign is not associative.
Right. Yeah, that is the intuition, right?
Okay, ma'am.
But then I would suggest that you shouldn't go by it. You have to write it down and verify.
First one is actually some standard result on commutator product, I think.
Yeah, yeah. Yes. Okay, so this one you can go ahead and solve it on your own. Okay, another question on eigenvalues. So P is a 3 cross 3 matrix having eigenvalues 0, 1 and -1. Okay. Further, V1, V2, V3 are the eigenvectors corresponding to lambda 1, lambda 2, lambda 3. That is PV1 is lambda 1, V1 like that. PVI is lambda I, VI. Okay. Then the first entry in the first row and third column of P. Okay, so P is a 3 cross 3 matrix. You want P1, 3. Okay. So one way you can find all the entries of the matrix of P, right? Using these equations. If you know the eigenvalues and eigenvectors, you can find out what the entries of the matrix P are, right? But then you don't need all the entries of the matrix, right? You just want the first row and the third column entry. How are we going to get the third column of a matrix? We saw earlier, no? How do we get the third column of a matrix or the first
0, 0,
column
1.
of a matrix?
If I multiply 0, 0, 1.
Okay. For the third column, if I multiply the matrix with 0, 0, 1, I will get the third column of the matrix. And once I get the third column of the matrix, I know what is the first row entry there, right? If I get this is A, B, C, then this A is the first row, third column entry, right?
Yeah. So basically, we have to write the 0, 0, 1 as a linear combination of these V1, V2, V3.
Yeah, that's it. I don't know what is P. I know what is P of Vi. That is, I know P of 1, 0, 0, 1, 1, 0, 1, 0, 1. But I don't know what is P of 0, 0, 1. But I can write it as a linear combination of these two vectors, right? Or all the three, I think. No. First and third. V1 minus V3.
Yeah, first and third.
Or V3 minus V1. V3 is 1, 0, 1. V1 is 1, 0, 0. Right. So when I subtract these two, I get 0, 0, 1. So I have this. So I just have PV3 minus PV1. What is PV3? Lambda 3 V3 minus PV1 is lambda 1 V1. But lambda 1 is 0, so this term is 0. Lambda 3 is minus 1, so this is minus V3. That's it. So P0, 0, 1 is minus V3. Minus V3 is 1, 0, 1. So I want the first row, third column. This is the third column of the matrix. Third column is minus 1, 0, minus 1. I want the first row entry here, which is minus 1. Right? So we have that as an option.
Yes.
So ma'am, what to do if the given vector is not a linear combination of the eigenvectors?
Okay, in that case, you cannot do anything. But then this is an MCQ question, and they also know that you shouldn't be spending much time on the question, right? So you see that the three vectors are linearly independent, right? So any vector can be written as a linear combination of them. It will mostly be given like this, and not just that. See, the diagonal, the eigenvalues are all distinct, which means that the matrix is diagonalizable. And it is diagonalizable means every element, every vector can be written as a linear combination of the eigenvectors, right? The eigenvectors span the entire space, R3 here.
Ma'am, why you took V3 minus V1 there?
Because I want the third column. See, I know that if I multiply with 0, 0, 1, I will get the third column of the matrix, right? To get this 0, 0, 1, I'm seeing how I will get 0, 0, 1 using V1, V2 and V3.
Ma'am, this means you are taking like an identity matrix. Then there the third column is like third column is like 0, 0, 1. So you are doing is that you are multiplying P from the third column of the identity matrix like this, right?
Okay, yes. If you do that, you will get the third column of the matrix. See, the other problem we saw, no? If you multiply a matrix with 1, 0, you're going to get the first column of the matrix. If you multiply it with 0, 1, you're going to get the second column of the matrix.
Oh, okay, ma'am.
So this is for a 2 cross 2 matrix. If you take 3 cross 3, you will take the... In fact, you will be choosing the columns of the identity matrix only.
Okay, ma'am.
To get the corresponding columns. Okay, so I think this problem is clear. Okay, so 2023 MCQ again. Again, you have eigenvalue problem. So you have a matrix A, and then B is A power 5 plus A power 4 plus identity. Which of the following is not an eigenvalue of B? Okay, so first of all, what are the eigenvalues of A?
Three, 0, 0.
Okay, it is straightforward that 0 is an eigenvalue.
One of the eigenvalue is 0.
So because determinant of the matrix is 0, right? One entire row is 0. So determinant is 0 and determinant is product of eigenvalues. So if determinant is 0, then 0 has to be one of the eigenvalues. Product of eigenvalues is 0. So at least one of the elements has to be 0. So 0 is an eigenvalue. Another thing is trace is sum of the eigenvalues. Okay. So 0 is one of the eigenvalues. How do I find the other eigenvalues?
110 is an eigenvector for another 0. Ma'am, 110 is an eigenvector for eigenvalue 0.
0.
And 010 is another eigenvector.
0, 1, 0. Oh, you're saying eigenvectors
no,
of
ma'am.
0. Okay, okay.
No.
Or of what are you saying? These are eigenvectors of?
First one is eigenvector for eigenvalue 0.
Okay.
That's all, ma'am.
The second one is not an eigenvector, right?
Yes, ma'am.
But you can think of 0, 0, 1. 0, 0, 1 gives the third column, right?
Yes, ma'am.
And that is 0, 0, 2.
Yeah.
So 2 is an
2 is
eigenvalue.
an eigenvalue. 2 is an eigenvalue also.
Yeah. 0 is an eigenvalue because determinant is equal to 0. 2 is an eigenvalue because of this reason. 2 times 0, 0, 1. See, if any column of the matrix is a multiple, is a scalar multiple of the standard
Basis. Standard order basis.
then it will be an eigenvalue, right? See, for this reason. If you multiply with 0, 0, 1, you're going to get the third column. And the third column is a multiple of 0, 0, 1, right? If it was the second column, you could have chosen 0, 1, 0 accordingly. So whichever column is an a multiple of the standard basis vectors, that corresponding to that, whatever is that number, that is going to be an eigenvalue. So for this reason, 2 is an eigenvalue. And I have 2 of the eigenvalues. So I can use the trace and then find the other eigenvalue. 0 is an eigenvalue, 2 is an eigenvalue, lambda 3 should be equal to 1 plus 0 plus 2. Right? This is 3. So what is lambda 3? 1. Right? Or did I make a mistake? Lambda 3 plus 2. 2 gets cancelled. Lambda 3 is 1. Yeah. So the eigenvalues of A are
0, 1 and 2.
0, 1 and 2. So now what can we tell about the eigenvalues of A power k? 0 power k, 1 power k and 2 power k. So it is what? 0, 1 and 2 power k. So the eigenvalues of A power k are all going to be this. So eigenvalues of A power 5 will be 0, 1, 2 power 5, that is 32. 32. Eigenvalues of A power 4 are 0, 1 and 16. Right? So here, A power 5 and A power 4. What are the eigenvalues of I? They are 1, 1, 1. So you have the eigenvalues of these three matrices.
2 will be the option.
Okay, yeah, 2. Okay. So in general, eigenvalue of A plus eigenvalue of B need not be an eigenvalue of A plus B. Right?
Yes.
This is not true in general. But if you take powers of A, say A power k, an eigenvalue of A power, say, m will be an eigenvalue of A power k plus A power m.
I think this, madam, the more generalized result we can write like this. Let's say lambda is an eigenvalue of A. Then for any polynomial Px, P lambda will be the eigenvalue of the matrix Pa.
Yes, that is the spectral theorem.
Yeah.
Right. So, and eigenvalue of A plus eigenvalue of the identity matrix. You can do this also. A plus identity matrix. So in general, as he mentioned, eigenvalue of P of A will be same as P of eigenvalue of A, where P is any polynomial. So if I look at the eigenvalues of A power 5 plus A power 4 plus identity, this will be the same as applying the polynomial P on the eigenvalues of A, where P of X, what is the polynomial? It is X power 5 plus X power 4 plus 1. So I just have to apply this polynomial on the eigenvalues of, on the eigenvalues of A, in fact. On the eigenvalues of A, but then I have listed down, no, A power 5, eigenvalues of A power 5, eigenvalues of A power 4, and eigenvalues of I. So you just have to add them. So
1
1
and
3
49.
and something, whatever this is. Okay,
49.
this is 49. So these are the eigenvalues of A power 5 plus A power 4 plus I. You just have to pick which is not an eigenvalue. So 1, 3 and 49 is gone. So 2. 2 is not an eigenvalue of B. So this is the more general thing that you have learned from this. Okay, is it clear to anyone? Any questions on this? It is easy to prove this using the AX is equal to lambda X. You can just show this. Okay. So in 2024.
Ma'am, here, if we have a matrix whose second column is suppose 0, 1, 0, or second column is suppose 0, 3, 0, then one of the eigenvalue will be 3 now?
Yes. For the second column, it has to be the second basis vector. For the first column, it has to be the first basis vector, like that. So in this case, 3 is an eigenvalue.
If first column is 0, 3, 0, then?
We cannot say anything.
Means ordered basis is 1, 0, 0, 0, 1, 0, 0, 0, 1.
Yes.
Then
Yes.
numbering of the column will be same.
Yes. Because for the first column, to get the first column, you have to multiply with 1, 0, 0, no?
1, 0, 0, yes, ma'am.
So in the second, if you have this, you're going to get 0, 3, 0. Then this is not going to be an eigenvector, no? That's right.
Okay, okay, thank you, ma'am.
Okay. Okay, so 2024 Madras. So A is given to be this vector. It is a vector in R4, 4 components, 1 by root 3, minus 1 by root 2, 1 by root 6, and 0. Consider the following two statements. So the matrix I minus A transpose. So A is a 4 cross 1 vector. So A transpose is a 4 cross 1, 1 cross 4. So 4 cross 4 matrix. So I have a 4 cross 4 matrix A transpose, and then I minus A transpose I have to calculate, and then I have to check whether it is invertible or not. Not just that, I have to do that for 2 AA transpose also. So what do we do here? What is the connection between eigenvalues and invertibility?
0 should not be an eigenvalue.
All eigenvalues are non-zero.
Yeah. So if all the eigenvalues of AA transpose are non-zero, then I know that, okay, I can tell about AA transpose. But then AA transpose is a 4 cross 4 matrix. So what do we do?
In A, we have the last column, last entry as 0.
Right.
So the last column of the 4 cross 4 matrix will be 0.
A transpose, right? Okay, but then I only know about this matrix. No, I also want to know I minus. So because of I minus, that entry will become 1, no?
Yeah.
What
I
can we
think
tell about the eigenvalues of AB and eigenvalues of BA?
A non-zero eigenvalue.
Same. They are same.
The non-zero eigenvalues of AB and BA are same, right? Non-zero eigenvalues. They are the same. In fact, including multiplicity, they are the same, right? So now, if I want
And
to...
then it also means that all the eigenvalues are same, right? Non-zero eigenvalues being same as saying all the eigenvalues are same.
See, if 0 is an
No, no.
eigenvalue,
that is not true. If
they
their
may
order
be
are
different
are
orders. No?
different, then only non-zero eigenvalues are same with multiplicity.
Their orders need not be the same. Their ranks need not be
Means
the
if
same.
we have two matrices A and B, and AB is a matrix and BA is a matrix, and AB and BA have order different, then non-zero eigenvalues of AB and BA are same up to, sorry, with multiplicity also.
Non-zero eigenvalues of AB and BA are the same.
With
Will it
multiplicity
be up
also.
to multiplicity also? Ranks need not be the same, no? I don't think
Rank
multiplicity.
need not be same.
So if
A and B
ranks
are
is not the
square
same,
matrices, then the eigenvalues are same. That's what it is. Okay.
yeah. Okay, AB and BA should be well defined. Both are square matrices, then I can calculate their eigenvalues. Their non-zero eigenvalues will be the same. In the sense that if 1, 1, 2, 3, 0 are eigenvalues of AB, then I know that 1, 2, 3 will be eigenvalues of BA as well. In fact, 0, AB. If determinant of AB is 0, then determinant of BA is also 0, right?
Is the non-zero eigenvalues with
Non-zero eigenvalues have
multiplicity
same
same?
Okay, you
multiplicity.
cannot say that. You cannot say that because A and B, AB need not be inverted. Square. Okay, fine. What is it?
If A and B are both square matrices.
I was saying algebraic multiplicity as same. Sorry, you continue.
Okay, if A and B are square matrices, then 0 is an eigenvalue of AB means 0 is an eigenvalue of BA as well, right?
Yeah,
Yes,
you
yes.
said the non-zero eigenvalues of same multiplicity are the multiplicity is also same. Then the set of all eigenvalues are same for square matrices.
For square matrices. Right. For square matrices, for both to be defined, both have to be of the same order.
Yeah.
Okay.
In that case, AB and BA all are eigenvalues.
Eigenvalues will be same, right? Okay. So yeah, how am I going to use that here?
So A transpose A will be a real number, so that will be an eigenvalue, non-zero eigenvalue of the matrix A transpose.
Yeah, that's it. So A transpose A is just a 1 cross 1 matrix, so it is just a number. So we just have to calculate what is A transpose A. A transpose A is what? It is nothing but sum of square of all the entries of the vector A, right? 1 by 3 plus 1 by 2 plus 1 by 6 plus 0. So this is 1. So 1 is an eigenvalue of A transpose A, which means 1 is an eigenvalue of A transpose. In fact, we are interested only in non-zero eigenvalues, right?
Yeah.
Yeah, because I know the eigenvalues of I are 1. In fact, I am interested only in the eigenvalue 1, right? Because only when 1 is an eigenvalue of AA transpose, it is going to affect the invertibility of I minus AA transpose. Okay, so we know now this is not true and this is true, right?
Yes.
Yeah. So 1 is an eigenvalue of I. So for I, you have eigenvalues 1, 1, 1, 1, 4 times 1. And for AA transpose, you have an eigenvalue 1. In fact, that is the only non-zero eigenvalue. So when we talk about the difference, it is going to be 0. For 2 times AA transpose, the eigenvalue is going to be 2. So the difference doesn't become 0. 1 minus 1, whatever. So we are just bothered about invertibility. We don't want a 0 to be an eigenvalue. That is, we don't want 1 to be an eigenvalue of AA transpose. But that's happening, so this is not invertible. But for 2 AA transpose, it is not an eigenvalue.
Ma'am, but for we just know about one eigenvalue of AA transpose, which is 1. There could be half could be an eigenvalue of AA transpose.
No.
Then
All the non-zero eigenvalues of AB and BA are always the same.
okay.
So if AA transpose, in fact, AA transpose is a rank 1 matrix, right?
Yes.
Because it is generated by a single vector, right? So it will have only one non-zero eigenvalue, right?
Yes.
So it is that. It is the one which is which will be the eigenvalue for A transpose A. Same. Okay.
Ma'am.
Yes.
Ma'am, in the 7th number question, can you please again here I can see that A transpose and A transpose A, both of them has the same eigenvalue, non-zero eigenvalue is the same. Now, so the eigenvalue of A transpose A, you have we have calculated it as 1. Now, so eigenvalue of I minus A transpose will also will be the sum, or the will be we will subtract eigenvalue of I minus of eigenvalue of A transpose, right?
Yes. Yes.
So both are giving it 0. So means if it is 0, then it is not I can't understand why it is not invertible with the eigenvalue concept.
So invertible means what? Determinant of the matrix
Determinant is non-zero.
Determinant of A is equal to product of eigenvalues of A.
Yes.
So if 0 is an eigenvalue of A, then the determinant becomes 0, no?
Oh, okay, ma'am. Okay, ma'am. Okay, ma'am.
Yeah.
Okay.
Okay. This is another question, MSQ. So multiple correct answers, 2024 Madras. For a matrix M, let row space of M denote the linear span of rows of rows of M, and column space denote the linear span of columns of M. Which of the following holds for all ABC 10 cross 10 matrices satisfying AB is equal to BC? Okay. So A is equal to BC. So irrespective of the order of the matrices, in fact, in general, for M, N, R, this will be true. Whatever we are going to deduce will be true. So you have A is equal to BC. You want to see what is the relation between the row space of A and row space of B or C, column space of A with column space of B or C. Okay. So first of all, what is the column space? Column space is the span of the columns of the matrix. So column space is span of columns. Column span is column space. And row space is span of the rows. But when we are doing, okay, is it easier to deal with rows or columns?
Rows, I think.
We write the vectors as columns, no? Any vector as
Okay,
a
yeah.
column vector. So
Yeah.
columns are easier to handle. So can you see that the row space of A is the column space of A transpose?
Yes.
Yeah. So if to understand about the row space, I can take the transpose of the matrix and see what is the relation. And to understand the column space, I can just directly deal with the columns. Okay. So now, when do we say an element is in the column space? X belongs to column space of A. Then X is a linear combination of columns of A. So what can we tell about X? Can I write there exists a Y such that X is equal to AY?
Yes.
Right? Because when I multiply a matrix with a vector, say I have a 2 cross 2 matrix, when I multiply it with any vector, what am I getting? AX plus BY, CX plus DY. I can always write this as X times AC plus Y times BD, right? So I'm taking the columns of the matrix and I'm doing linear combination. Whatever is the entries of the vector that I'm multiplying with that I'm doing a linear combination of the columns of the matrix. So whenever a vector is a linear combination of the columns of the matrix, I can just find another vector such that X is equal to AY. This is called the range space, right? Range of a matrix. Yeah. So we can write it like this. So now what I want to prove is, if I want to check this. If X is in column space of A, can I tell that X belongs to column space of B? Or can I tell that X belongs to column space of C? That is what I want to see. So X is in column space of A means X is equal to AY, but A is equal to BCY. Now, what can I conclude? Is it in column space of B or column space of C?
Column space of B.
Yeah. Because I can write this as B times CY. I can take this CY to be some Z, right? So this is some BZ, which means that X is equal to BZ for some Z. In fact, we know what that Z is. It is equal to CY. So this means X belongs to column space of B. But I cannot tell something like this for the column space of C, right?
Yes.
Yeah. The range of this matrix and this matrix will be the same, and the null, not same, contain. And there is a relation between the nullity of this null space of this matrix and this matrix. Whatever is the outside matrix, that is associated with the range of the matrix, and whatever is inside is associated with the null space. So if the same question was asked about null space, then the relationship would have been with A and C. Okay, because it is column space of A is contained in column space of B. So we started with an element in column space of A. We proved that it is in column space of B. So column space of A is contained in column space of B. There is no relationship between A and C. You can give matrices where it is not, the containment is not true. Now that we have done for column space, we needn't do anything for row space, right? We know the relationship between row space of A and column space of A transpose. A is equal to BC implies A transpose is equal to C transpose B transpose. And with what we just proved, we know column space of A transpose is contained in
Column
column
space of
space of C transpose. But column space of A transpose is row space of A. This is contained in column space of C transpose is row space of
C.
So row space relation is this. This is not there. Is it clear what we did? Does
Yes.
anyone have a question? Okay. No response, I assume no questions.
Sir, madam, if the relation was for the null space, then the statement will be the option will be other two, I think.
No. Other two in the sense you cannot. Okay. Let me just show you. So if I take the null space of.
Then null space of C is a subset of null space of A.
Yeah. So null space of A and null space of B, null space of C. What is the relation? So if I take any element X in null space of A,
C.
It means AX is equal to 0. It means BCX is equal to 0. And then what can we tell? We cannot conclude anything from here.
We have to take X belongs to null space of C.
You have to take the other way around. So let X belongs to null space of C. Then I know CX is 0, which means BCX is 0,
So
which
AX
means AX is 0. So X belongs to null space of A. So null space of C is contained in null space of A. So when it comes to null space, it is the inner matrix that this one, C. For the range space, it is the outer matrix, B. The relation is with B.
Yes.
Okay. This is an NAT question, 2021. Determinant of the matrix. I guess you can solve this, right? You can use the rules for determinants being equal. So the determinants of two matrices are the same if you take those elementary row operations that you perform, right? If you replace any row with alpha times the row, the determinant gets multiplied with alpha. Determinant gets multiplied by alpha. And then if you replace a row with a linear combination, row 1 plus alpha times Si, then the determinant remains the same. There's no change in the determinant. Those elementary row operations that you can perform, right? Using that, you can simplify this and calculate the determinant, right? Any questions on this? If you know this, we can skip.
Yeah. We can skip this.
Yeah, see, there is a pattern. If you do the elementary row operations, it will all reduce to some simple matrix. Then you can find the determinant. Here. Let A be this matrix. Then the largest eigenvalue of A is.
From here we can find eigenvalues because row sum is
same.
Row sum is 4.
So if the row sums are equal, then that is an eigenvalue. This is an eigenvalue. Same with column sums, right?
Yes.
Yeah, because when I multiply the matrix with 1, 1, 1, what I'm doing is I'm just adding all the entries of each row. If all of them turn out to be the same number, if it is alpha, 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 then I can write it as alpha times 1, 1, 1, right? So the row sums, if all the row sums are equal, then that whatever is that equal value, that is an eigenvalue. So you can see that 2 minus 1, 1 plus 3, 4. 4 is the row sum for each row. So 4 is an eigenvalue. Is there any other eigenvalue that we can identify?
0 is an eigenvalue and -4 is another eigenvalue.
Okay, 0 an eigenvalue, determinant is 0, is it?
First two rows are equal.
Oh, the first two rows are equal, right? When two rows are equal, then the determinant, not just equal, scalar multiples of each other, which means that the determinant is 0. So 0 is another eigenvalue. And we know that trace is sum of
We can use
eigenvalues,
trace
right?
here.
2 minus 1. This is the trace. This is
0.
what? 0. This is equal to 4 plus 0 plus the third eigenvalue. So lambda 3
4
is
will be the
minus 2. So we have all the three eigenvalues. The largest one is 4. Okay, fine. So in such problems, mostly it will not be calculating the eigenvalue in the traditional way. So there will be like this one, row sums are equal, determinant is 0 just by observation. So all these things we shouldn't miss. And so you can find the eigenvalues by using those methods. Okay, another NAT. A is given to be this matrix. A transpose denotes the transpose of the matrix. You have two vectors, U and V, be column vectors with real entries such that U1 squared plus U2 squared is 1. V1 squared plus V2 squared plus V3 squared is 1. That is, both are unit vectors. And suppose AU is equal to root 2V, A transpose V is equal to root 2U, you have to calculate something. Okay. I don't know any other way of calculating this other than traditionally solving these two equations. If you know some other way, you can tell. Otherwise, I think we can quickly do it. So this is again a problem where you have to make sure that you're writing clearly so that if you miss out on something, you can V1, V2, V3. So this is U1 plus U2 is root 2 V1. U2 is root 2 V2 minus U1 plus U2 is root 2 V3. Okay. And the other one is A transpose V. 1, 0, minus 1, 1, 1, 1. V1, V2, V3 is root 2 U. U1, U2. So this is V1 minus V3 is root 2 U1. V1 plus V2 plus V3 is root 2 U2. Okay. So is there something that we can do to simplify? So see, when we add these two equations, we get 2 times U2 is root 2 times V1 plus V3. Then what do we want? We want U1 and U2. Oh, U1 and V1. Okay. Then maybe I will just cancel this out. I have V1 plus V3 is root 2 U2. And I have V1 minus V3, that is root 2 U1. So when I add both, I'll get 2 V1 is equal to root 2 times U1 plus U2. Oh, but that is root 2 U1. I get V1 is equal to V1. That's not going to help. Can we get rid of V2 here? Okay, when I add these two, oh, that's not going to help.
If I add first and third, then U2 is equal to root 2V.
First and third, U2 is U2, when you add these two, you're saying this is what we get, no? 2 root 2 times U2 is V1 plus V3.
So V2 is equal to 0.
Oh, we can substitute that here, right? We can substitute this here and we get V2 is 0. And if V2 is 0, U2 is 0 from here. And if U2 is 0, U1 is root 2 V1. But from the third equation, I also have U1 is minus root 2 V2. Is it right? It shouldn't be right. Oh, not V2, V3. So I get V1 is equal to minus V3 and V2 is 0. And I know that V1 is a unit vector, right? V1 squared plus V2 squared plus V3 squared is 0. So V1 squared plus V2 squared plus V3 squared is V1 squared. Oh, sorry, this is equal to 1. So I know V1 is 1 by root 2. So V3 is minus 1 by root 2. And once I know V1, this implies U1 is root 2 times V1. So that is 1. And U2 is already 0. So U is 1, 0. V is 1 by root 2, 0 minus 1 by root 2. From this, we can find out this value. U1 is 1. V1 is 1 by root 2. So I think this is 3. Yeah, this is 3. Okay, fine. So we just had to play around with the equations we had. I don't know any other way to solve this problem. So if you know, then fine. Again, a determinant problem. It has a pattern. So you just have to use those elementary row operations and then reduce and find the determinant.
Madam, can we go to the last problem? Can we calculate the inner product way to calculate the modulus? Inner product of U1 plus 2 root 2 V1, comma, that one. Norm of U1 is given, norm of V1 is given. But U1, V1 inner product, we have to find it. Can we find it?
Inner product is what? Inner product AU with V is same as inner product U with A transpose V.
Yeah.
Right? AU is root 2 V. This is equal to U with A transpose V is root 2U.
Yeah.
So this is, but we get norm U squared is equal to norm V squared. That we know, no? It is equal to 1.
No, madam, I'm not saying this. I'm saying that start with that modulus square. That mod U1 plus 2 root 2 V1 whole square. So that is equal to inner product of U1 plus 2 root 2 V1, comma, U1 plus 2 root 2 V1. So that will be.
No, but this is a number, no? I think you have to do inner product U with 2 root 2 V. Maybe take the whole vector.
Modulus of V is basically inner product of V comma V whole square.
Yes, but then this is not a vector, no? This is just the first element, no?
Yeah. That is U1, V1. Yeah. Sorry. Yeah.
But I think this has to do something with inner products. Otherwise, it shouldn't be. I don't know. Maybe we are missing out on something. I couldn't see how this is associated with the inner product, but it makes sense to talk about inner products, because why will I sit and solve such equations? There should be something behind it.
Okay. Okay.
Okay. This determinant question, I guess you can do. The maximum number of linearly independent eigenvectors. This is equal to the rank of the matrix, right? Rank of the matrix is nothing but the number of linearly independent eigenvectors, right? So you just have to calculate the rank. In fact, this is a block matrix. Rank of this is 2 and rank of this is 1. Right? Both the rows are linearly dependent. So total rank is 3. Right?
Yes.
You just have to know this. Otherwise, you can also use the Jordan decomposition and find, you can easily tell from the matrix. But in general, rank is the number of linearly independent eigenvectors. So you just have to calculate the rank.
Ma'am, I have a doubt in previous question.
This
Ma'am, if we have second row as 2, 3, 0, 0, for example, if we have second row 2, 3, 0, 0, then the above block matrix is diagonalizable, but the matrix 3, 0, 1, 3 is not diagonalizable.
Yes.
But here rank is 4, but linearly independent eigenvectors are not 4. So how can we see that rank is equals to number of linearly independent eigenvectors?
Madam, can you repeat the question? If that number is instead of 2, 3, then what will be your question?
Here the matrix 1, 1, 2, 3 is diagonalizable, but the other block matrix 3, 0, 1, 3 is not diagonalizable. So, but here rank is 4. Now here rank is 4. So how can we say that rank is equals to number of linearly independent eigenvectors?
Ma'am, I have a related doubt. Like if we are taking the 0 matrix, then the entire space will be the eigenspace corresponding to 0, right? But then rank of 0 matrix is 0.
If I take the 0 matrix, then its rank is 0, okay? What are you saying?
But then the maximum number of linearly independent eigenvectors need not be 0, right?
Actually, madam, the maximum number of linearly independent eigenvector may not always be equal to the rank.
Is it?
Yes.
Maximum number of linearly independent vectors in the column or row, that is actually rank. But
right. Okay, it's eigenvectors here. Right. My bad. It was wrong. Oh, the max. What did I say? Rank is right. It is the number of linearly independent columns of the matrix. Right. Fine. Sorry. My bad. So here they're asking for the maximum number of linearly independent eigenvectors. Right. Okay. So in this case, eigenvectors corresponding to distinct eigenvalues will be linearly independent, and then I have to see when it is repeated. Okay, so eigenvalues here are 3, 3. Here it is determinant is 0, so 0 is an eigenvalue. Trace is 3, so 3 is another eigenvalue. So this part is diagonalizable, right?
Yes.
So here I will have two linearly independent eigenvectors. So here I will have two linearly independent eigenvectors. And from here, how many? This is not diagonalizable,
Here
right?
we have one linearly independent eigenvector.
Here I have, right, because this is not diagonalizable, right? One linearly independent eigenvector. Sorry. It was my bad. I was thinking of linearly independent columns. Rank is number of linearly independent columns of the matrix, right? Okay. So because this part is not diagonalizable, so you will be able to get only one linearly independent eigenvector from this. This is in the Jordan canonical form, right? So there is a 1 here, so you will get only one linearly independent eigenvector from here and 2 from here. So this is equal to 3. Right. Okay, thank you so much for pointing out.
Ma'am, can you please explain the last part? Like, can we say that any lower triangular matrix or any upper triangular matrix is not diagonalizable?
No, not like that. It is in the Jordan form, no? That is why. If it was like this, then this is in the Jordan canonical form, right? This or the transpose of this matrix. So if it is like this, it means that you will have only one linearly independent eigenvector for this entire block. Now, if there was a 0 here, then you can split it like this. This is a diagonal block. This is another diagonal block. This is in the form where you have a 1 here. So for this block, you will have one linearly independent eigenvector. For this block, you will have one linearly independent eigenvector. So this is when you have a Jordan decomposition, for each block, you will have a linearly independent eigenvector. If you have different eigenvalues, then no problem, right? Then it is diagonalizable. Distinct eigenvalues means the matrix is diagonalizable. There is a problem only when there are repeated eigenvalues. If it is a repeated eigenvalue, if you can write it in this diagonal form, then again you have for each part, you have a linearly independent eigenvector. If you cannot put it in this diagonal form, if you can write it like this, then for this block, you will have a linearly independent eigenvector. And any matrix has a Jordan form. You can write a Jordan form for any matrix where all the diagonal entries of the matrix will be the eigenvalues of the matrix. And for repeated eigenvalues, for each block, for each corresponding block, you have a linearly independent eigenvector. So instead of a 1 here, if you had a 0, then you will have two eigenvalues corresponding to linearly independent eigenvectors corresponding to this. So the thing is, you have to try to split it into blocks, diagonal blocks. Smallest diagonal block is 1 cross 1. When you can split, when the matrix is diagonalizable, then it can be split into 1 cross 1 diagonal blocks. When the matrix is not diagonalizable, it means that there are going to be ones somewhere, either in the lower triangular part or in the upper triangular part. And whenever there is a 1, that block will correspond to one linearly independent eigenvector. Is that clear?
Ma'am. Ma'am, here the first matrix we have 1 1 2 2. Here we got the eigenvalues 0 and 3. The second one we got 3 and 3. The question is that maximum number of Li eigenvectors. So ma'am, here we are getting 3. Ma'am, so how can we get the linearly independent eigenvectors? Can you please explain again here?
So the first block 1 1 2 2, that block has two distinct eigenvalues, right?
Yes.
So if it has two distinct eigenvalues, it is diagonalizable, right? So
Ma'am,
that
can you
block can be
explain
written
without
as
using diagonalizable concept?
corresponding to distinct eigenvalues. You have linearly independent eigenvectors, right?
Yes, yes.
So corresponding to this and this, you will have one linearly independent eigenvector.
Yes.
And then now you have this block, the 3, 3.
Yes.
So for this, okay, you don't want Jordan block.
Yes, yes.
So if you don't want the Jordan block, then because of this one, there'll always be a relation between the eigenvectors corresponding to this. So 3, 0, 1, 3. What is it? 3 is an eigenvalue, right? So we
Yes.
know that this is say V1, V2. This is equal to 3 times V1, V2. So the relation that you get is 3V1 is equal to 3V1. V1 plus 3V2 is equal to 3V2. Right? Have I written it correctly? A B is equal to lambda V. Right. So, what is the null space of AV minus lambda V? This is going to give you the geometric multiplicity, right? Algebraic multiplicity of 3 is 2.
2.
This is going to give you the geometric multiplicity of 3, the eigenvalue 3, right? So null space of AV minus lambda V is, null space of A minus lambda I. This is going to give you the geometric multiplicity of lambda, and that is null space of.
We can simply calculate A minus 3i. It is 0, 0, 1, 0, which is not exactly 0.
This is equal to 1, right? The null space, nullity. So the geometric multiplicity of 3 is 1. And the algebraic multiplicity is 2. Algebraic multiplicity is 2 because of this. The geometric multiplicity is 1 means that it has only one linearly independent eigenvector corresponding to the eigenvalue 3.
Oh, okay, ma'am.
Right. So, right, the geometric multiplicity of the eigenvalues give you the corresponding what is the number of linearly independent eigenvectors that you get. So for this block, you get only 1. In this block, because they are distinct eigenvalues, you will get 2. Because algebraic multiplicity of 0 is equal to 1, geometric multiplicity is less than or equal to algebraic multiplicity, but this is already equal to 1, so geometric multiplicity will also be equal to 1. Similarly for 3 in the upper block. So when you have distinct eigenvalues, the algebraic multiplicity, geometric multiplicity will be equal to 1. So you will get linearly independent eigenvectors from there. When you have repeated eigenvalues, there you calculate the geometric multiplicity. That's going to give you the number of linearly independent eigenvectors. Is it clear?
Yes, ma'am.
Ma'am, I want to say something.
Yes.
Ma'am, here, ma'am, please scroll down. Ma'am, here we have matrix 1, 2, 1, 2, block matrix 1, 2, 1, 2. So here, suppose column vector AB and column vector CD are eigenvectors of this matrix, this block matrix. Then AB and 0, 0, AB 0, 0. Please write column vector AB 0, 0 is the eigenvector for the matrix of this 4x4 matrix.
Yes.
Is it correct?
Yes, yes.
Okay, ma'am.
Okay. This is the 2024 NAT. I think you can do this. You have to calculate the 4-1 entry of M inverse. Okay, I don't know if there is any simpler way of doing it. But I think I will just calculate the inverse. Means you didn't need to calculate the entire inverse. You just want the determinant and the cofactor corresponding to 4-1, right? Or 1-4, whatever.
Ma'am, please repeat.
M inverse is what? 1 by determinant of M into adjoint of M, that is cofactor transpose. You take the cofactor matrix and take the transpose. So if you want the 4-1 entry of M inverse, that is going to be the cofactor of 1/4 entry, right? So the cofactor of 1/4 entry is 1/4. This entry is the determinant of this matrix. Minus 1 power 1 plus 4 into determinant of 1, 0, 1, 2, 1, 0, 3, 2, 1. And then you have to multiply this entire thing, means divided by the determinant of M.
Ma'am, isn't the given matrix symmetric? So will that have something to do with the value?
I don't know. It's symmetric, so. But then I don't need anything else here, no related to symmetry. Determinant. And the diagonal entries are all 0. And it is a nice looking matrix. Maybe you can use row reduction to get the determinant in a simpler manner. But I don't know if it plays any role here. Determinant of this matrix, I think you can expand along this row and get easily. But then for this, I don't know, maybe it's just with some row reduction or something that we can do to get the determinant.
Yeah, now let us move for a feedback. Yeah.
Madam, how to get that PDF? How we will get that PDF?
Yeah, we will share through our groups along with the recordings of this session. You can join Math Aspirants. If you are not a member, you can just WhatsApp me. Okay, thank you, Dr. Sushmitha, for being with us. For
Sir,
this
I have
very...
joined a group. Group name is 𝐶𝐬𝐻 GRF IIT JAM discussion.
Yeah, there is a there is a Math Aspirants group. You can, I will text my number in the chat box. You can
that will be good. Please,
yeah,
please.
you can WhatsApp your details to that number so that I can add you to our group. Okay, thank you, Sushmitha, for this nice session with a good collection of problems. And I have noticed that the session is really engaging. Our participants are really actively participating in the discussion. So, yeah, I'm sure that all of them have really benefited out of our program.
Yes,
and
sir.
also,
Thank you so much, ma'am, for your
Yeah,
valuable
thank
time.
you for pointing out. I made a blunder and thank you for pointing that out.
Yeah, that may happen because we are not doing this type of problems in a regular basis.
Yeah.
Okay, dear participants, feel free to share your feedback now. You can just turn your video on and you can introduce yourself and share your comments about today's session. That will be very interesting and helpful for us to arrange more such sessions. And also our speaker also would like to hear from you. Yes.
Sir, please
Yeah.
share number again.
Yeah, I have sent it in the chat box. That number, I have shared it in the chat box. So, yeah.
Hello, madam.
Yeah, yes, Rajkumar.
Yeah, I'm Rajkumar Naik. I'm working as an assistant professor in �C𝐞𝐚𝐽 Institute of Technology in Malda. And it was a very nice session. And I have engaged, I have also some point of view on these linear algebra, some problems regarding like today. If you multiply with a matrix with some standard EI standard basis vector, and you will get that column. So I didn't realize that thing previously. So it was very nice, and your way to looking all these problems, it is very nice. And I am actually eager to see such kind of problem solving session on functional analysis, since I am also interested in, actually I am a person in functional analysis, so I want to see that kind of sessions in future. So that will be much more helpful for me also and all other functional analysis aspirants. And
Ma'am,
Yeah,
yeah,
thank you.
thank
Thank
you.
you, Rajkumar. 1 minute,
I
Niharika.
want a session. I
Niharika,
want a
1 minute.
problem solving.
Thank you, Rajkumar, for your wishes and your comments. We will try to organize more such sessions. On the coming Sunday, we have a session on real analysis. If you are not a member, please join our WhatsApp group so that you will get all the updates.
Okay. I'll join it. Okay. Thank you. Thank you, sir.
Yeah, yes, Niharika, you may continue.
Ma'am, actually, I want any problem solving session for inner product spaces. It is very weak part of mine of linear algebra.
Niharika, could you introduce yourself?
Yes, sir. Yes, sir. Sir, my name is Niharika. I am from Meerut city. I did my MSc from CCS University.
So please join our group. You will get all the informations regarding the future sessions. We try to organize more such sessions.
Okay, sir. In
Sir,
fact,
actually-
you will find the recordings of the previous sessions also. So
Yeah.
previously,
Yeah,
Ma'am, I'm not able to solve questions of inner product spaces. It is very weak topic of mine.
Okay. Thanks for your suggestion. We will try to organize such sessions. All the sessions so far we have conducted are uploaded in a YouTube channel. That also you can go through. I think by this time we have conducted, I think, around 200 such sessions. So you can go through it. Okay. Thank you, Niharika. Others?
Thank you, sir.
Sir, am I audible?
Yes, Praveen.
Hello, ma'am. My name is Praveen. I am a third year BSc Mathematics student at St. Thomas College, Thrissur. And this session was, I would say, fantabulous because the amount of effort that you have put in is like very much visible. First, you sorted the questions according to the year, then according to the topic. So thanks a lot for the amount of efforts that you have put in. And even the session, they were very much interactive. And you responded to our questions very well, and it was a very engaging session. So thanks a lot for this session, and I'm expecting more such amazing classes from you. Thank you, ma'am.
thank you, Praveen, and all the best for the upcoming exam as well.
Thank you, ma'am.
Yeah, thank you, Praveen. Okay, Praveen Mishra.
Good afternoon, ma'am. Good afternoon, sir.
Yeah.
I am Indresh Kumar from district Jalon in UP. I am mathematics lecturer in our district. I want to learn higher mathematics and I practice daily. Sir, your help is very good for us and our society. Thank you, sir, and thank you, ma'am. I learned some good approach for today in linear algebra.
Thank you.
Thank you, sir.
Thank you, Indresh Kumar. If any of you would like to share your feedback, please do it now. Yeah, I think. Yeah. Okay, once again, thank you, Sushmitha, for this nice session. I hope that you will be with math aspirants in future too.
Definitely.
Okay, once again, thank you everyone for this attending our program. Thank you.
Thank you. Thank you, sir.